electrons rotate only one nucleus. But in the molecule, the electrons rotate around more than one nuclei. If suppose it is a diatomic molecule, electrons rotate around 2 nuclei. If it is a triatomic molecule, electrons rotate around 3 nuclei. So that is the difference. In the atom, electrons rotate only around only one nucleus, but in molecule, electrons rotate around more than one nucleus. So the molecular orbitals are polycentric because these are rotating more than one nuclei. Electrons are fed into 3 molecular orbitals, one at a time, such that each entering electron occupies the lowest possible quantum state as per Aufbau principle. In the molecular orbitals also, electrons can occupy the lowest possible quantum state as per Aufbau principle. Also obeys Pauli's exclusion principle. Molecular orbitals are formed by linear combination of atomic orbitals. Linear combination of atomic orbitals like this. The molecular orbital theory describes electrons as delocalized moieties over adjacent atoms. It is powerful and has extensive approaches that extend beyond the limitations of the valence shell electron pair repulsion theory, Vesper theory, and valence bond theory. So, molecular orbital theory overcomes these problems. The Vesper theory and valence band theory accurately predict bond properties, but they fail to explain structure and magnetic properties of some molecules. Hence, the molecular orbital theory incorporates the wave character of electron in developing the molecular orbital diagram. These predict physical as well as chemical properties of molecule such as structure, bond energy, bond length, bond angle, etc. Also provide the information predicting molecules, electronic spectra, paramagnetism also. But in the valence bond theory and then Vesper theory, this we may not explain. So before going to theory, what is atomic orbital? What is molecular orbital? So the orbital is the region of space around the nucleus of a nucleus where the electron probability of finding of electron is more. Atomic orbital is the region of space around the nucleus of an atom where an electron is likely to be found or the electron density is more. Electron density is more. Molecular orbital. The molecular orbital is a combination of atomic orbitals where the region of electron density is most likely to be found in a molecule. Where the electron density is found, most likely to be found. So that is the difference between atomic orbital and then molecular orbital. So homonuclear diatomic molecules, in the sense molecules consisting of 2 same atoms. Example, hydrogen, oxygen, chlorine, nitrogen, like that. Heteronuclear diatomics are molecules consisting of 2 different atoms. Example, carbon monoxide, nitrogen monoxide, hydrogen fluoride, lithium chloride, etc. bonding molecular orbital and then anti-bonding molecular orbital, non-bonding orbital. Anti-bonding molecular orbitals are orbitals that are out of phase with each other are called anti-bonding orbitals. These are anti-bonding molecular orbital. This is in phase, then this is out phase. Out of phase. Orbitals that are out of phase with each other are called anti-bonding orbitals because regions with dense electron probabilities do not merge. So here electron possibility is here, then electron possibility density is more here. These two may not merge. That's why they may not form bond. So here electron density is here. Here electron density is here, more. Hence these do not merge. So orbitals that are out of phase with each other, out of phase with each other are called anti-bonding orbitals. Here regions with dense electron probabilities do not merge and may destabilize the molecule. There is no possibility to formation of bond. Hence, at the same time, these are high energy, destabilize the molecules. But bonding molecular orbitals are less energetic than anti-bonding atomic orbitals and are in phase. See here, both are in phase. Hence, these can be easily merged with each other. Bond will be formed easily here. So that is the difference between anti-bonding molecular orbital and then bonding molecular orbital. Okay. This is the electron density. Electron density. Phases, same here itself, just now we saw. Phases depends on their wave up or down displacements. Phases are designed in as plus or minus. So this is not indicated as a positive charge or negative charge. This indicated as a, if phase is upward direction, that we are showing for easily identification. We are giving positive sign here. This is in down phase. For remembrance, easy identification, we are giving the sign as a minus. But these are not indicating into the charge. These are phase. This is toward, this phase is towards up, this phase is down. Down we are representing with minus symbol. Upward phase we are representing positive, plus symbol. You have to remember it. A node occurs if the phase signs change from positive to negative or vice versa. Phase is probability of density of electron density is more. Suppose here, this is one phase, this is another phase, but here probability electron density is more, here also electron density is more. But node where the phase change from positive to negative. Here, this is the node. In between these two, this is the node. It represented as node. Are you understand? Phase and node. A node occurs if the phase signs change from positive to negative or vice versa. It is important to notice that the phase signs do not symbolic as a charges, as I explained. Nodes are regions where the probability of finding of an electron is 0. Exactly opposite to the orbital. In the orbital, probability of finding of electron density or electron is maximum. In the nodes are regions where the probability of finding an electron is 0. Okay. Here, in normal systems, in the molecular orbital theory also sigma bond and then pi bond is formed. The sigma bond is formed as end-to-end overlap, symmetric atomic orbitals. Pi bond is formed as a sideways overlap of atomic orbitals. So while constructing molecular orbital diagrams, the y-axis of a molecular orbital represents the total energy of the orbital. Individual atomic orbitals are arranged on the far left and far right of the diagram. Molecular orbitals formed by overlapping of atomic orbitals are located in the middle of the diagram. They overlap with each with either a sigma or pi bond with respect to their faces. They are designated as bonding, non-bonding, or anti-bonding orbitals. According to Pauli's exclusion principles, lower energy molecular orbitals fill first and then followed by consecutively higher energy molecular orbitals. So fundamental steps for constructing molecular orbitals. First, find the electronic configuration of each atom of the molecule and the place and the atomic orbitals for that atom. Determine if the molecule is homonuclear or heteronuclear. If the molecule is homonuclear, the atomic orbitals will be symmetric. Heteronuclear atomic orbitals will be slightly differ because the more electronegative atom will be placed lower on the diagram due to lone pairs of electrons being more stable and more electronegative elements. That's leading them to be lower in energy. Keeping in the mind energy of the atomic and then molecular orbitals, fill the molecular orbitals using energy and bonding properties of the overlapping atomic orbitals. You have to contribute to the positions of the molecular orbitals with respect to, suppose more nodes are there, more energetic, they are higher molecular orbitals. Sigma bond orbitals are stronger than pi bond orbitals. Anti-bonding molecular orbitals are higher in energy than bonding molecular orbitals. Constructive overlap is equal to less nodes, more stable, less energetic. You have to remember, whenever sigma bond is formed or constructive for constructive overlapping, there should be less nodes, less energy, hence they are more stable. Destructive overlap occurs whenever more energetic, more nodes, less stable. Actually, the number of individual atomic orbitals should be equal to the number of molecular orbitals. So with the molecular orbital diagram, we can predict properties of the molecule like bond order, bond angle, paramagnetism, etc. Actually, molecular orbitals are formed with linear combination of atomic orbitals. So, linear combination of atomic orbitals and then type of atomic orbitals. So, molecular orbital, as per Hund and Mulliken, a covalent bond is formed when two half-filled atomic orbitals of two atoms come nearer, come closer, and then overlap each other to form a new bigger orbital known as molecular orbital. Like here. like this. So one orbital with one electron, another orbital with another electron formed as a molecular orbital. Like this. Here. The two nuclei may approach each other along a line. When the nuclei comes close, the two atomic orbitals of the two atoms combine to form two molecular orbitals. One is bonding, another one is the anti-bonding orbital, like here. This is bonding, this is anti-bonding. This is atomic orbital of 1A, atom A. This is the atomic orbital of atom B. With this, one bonding, one anti-bonding molecular orbitals are formed. So anti-bonding orbital, molecular orbital which having higher energy gives rise to a repulsive state called anti-bonding. Molecular orbital which having higher energy with high repulsion is called anti-bonding orbital. Bonding orbital, the molecular orbital with lower energy with attractive state called bonding. This is the with attractive state, then lower energy, this is the bonding, this is the repulsive, and then higher energy, this is the anti-bonding orbital. Non-bonding orbital. Actually, these do not participate in chemical bond, they are inertial orbitals. Suppose if we are taking nitrogen atom, atomic number of the nitrogen is the 7, 1s2, 2s2, then 2p3 is the electronic configuration. 1s2, 2s2 may not participate in the 1s2 electrons and then may not participate in the bonding. Hence, they are known as non-bonding electrons. At the same time, which that orbitals, 1s orbital is known as non-bonding orbital. The forming of bonding and anti-bonding orbitals may be explained in terms of wave function. Psi indicates wave function. So here psi A represents wave function of the atomic orbital A, atom A. Psi B represents wave function of the atom B. So with this, one bonding, one anti-bonding molecular orbital is formed. You have to remember how many number of atomic orbitals are participated, then exactly equal number of molecular orbitals are formed here. This is the molecular orbital theory. We will take one example and then explain. Before going to that, spectroscopic measurement, the increasing order of energies of the molecular orbitals is decided in the following order. First, with spectroscopic measurement. With spectroscopy. So here, sigma 1s is greater than sigma star 1s, is greater than sigma 2s, is greater than sigma star 2s, is greater than sigma 2px, is greater than pi 2py, is equal to pi 2pz. These two are exactly equal. And then greater than pi star 2py equal to pi star 2pz is greater than sigma star 2px. This order is for homonuclear atoms, atomic number 7 and then more than 7. Also heteronuclear atoms. Heteronuclear atoms and then atomic homonuclear atoms more than 7 and then 7. Up to 7 means nitrogen onwards. First, after sigma 2px, pi 2py, pi 2pz will come. After that, pi star 2py, pi star 2pz, and then finally sigma star 2px will come. Then for homonuclear atoms, atomic number less than 7, sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, up to here same. But here for homonuclear atoms and then atomic number which having the 7 less than 7, pi 2 py is equal to pi 2 pz. This comes first. After that, sigma 2px will come. Sigma 2px will come. Then after that, as well as pi star 2py is equal to pi star 2pz is greater than sigma star 2px. You have to remember this order for filling up of the molecular orbital diagrams. Molecular orbital diagrams. Suppose if as per your syllabus, molecular orbital diagrams of nitrogen is there, and then nitrogen and oxygen. So nitrogen, molecular orbital diagram of nitrogen. So atomic number is 7. Electronic configuration is 1s2, 2s2, 2p3. Total number of electrons are 14 from 2 nitrogen atoms. But total number of orbitals are 10. This is 1 orbital. This is 2 orbital. And then from the p subcell 3 orbitals will come. From each atom 5 orbitals. From 2 nitrogen atoms 10 orbitals. 10 number of orbitals will come. Hence, electronic configuration is as follows. First, we will see the molecular energy level diagram of nitrogen. So, this is the y-axis represent energy. From one side, one atomic orbitals of one nitrogen atom. This side, atomic orbitals of another nitrogen atom. In between these two, these are the molecular orbitals. Molecular orbitals. So first I am explaining, I am taking, this is atomic orbital of one nitrogen, 1s2, 2s2, 2p3, 2px1, 2py1, 2pz1. Same thing from the another nitrogen atom, 1s2, 2s2, 2px1, 2py1, 2pz1. So while combining of the 1s orbital of one nitrogen atom and then another 1s orbital of the another nitrogen atom, it gives 2 orbitals. One is the bonding, another one is the anti-bonding. Bonding is sigma 1s2, sigma star 1s2. Same like the 2s from the 2 atomic orbitals of nitrogen, atoms of nitrogen. It combines and gives 2 bonding molecular, 2 molecular orbitals. That is the sigma 2s2, that is the bonding. Sigma star 2s2, that is the anti-bonding. Then here, 2px1, 2py1, 2pz1 of the each nitrogen atoms combined gives 6 molecular orbitals. But these molecular orbitals, pi 2py, pi 2pz, sigma 2px, pi star 2py, pi star 2pz, sigma star 2px. So as per Aufbau principle and then Pauli exclusion principle, here from these 2p3 electrons, from these 2p3 electrons, total 6 electrons are here. Pi 2py and then pi 2pz having the equal energy. Hence, first electron enter into these first electrons are filled with these orbitals equally. Pi 2py1, pi 2pz1. After that, pi 2py2, pi 2pz2. Then after filling these things, remaining 2 electrons are there. These 2 electrons enter into the sigma 2px. So while calculating the bond order, so bond order is equal to number of bonding electrons minus number of anti-bonding electrons by 2. So this is the bonding electrons from here to, this is also bonding 2, total 4. And then here to 6. This is to 10, 12. How many number of bonding electrons came here? Total 10. 10. And then anti-bonding electrons from here to, and then here to. Only 4 anti-bonding electrons will be there in the nitrogen molecule. So 10 minus 4 by 2 is the 3. Hence, triple bond is exist in between the nitrogen atoms of the nitrogen molecules. Nitrogen. This is the electronic configuration. Sigma 1s2, sigma star 1s2. Sigma 2s2, sigma star 2s2. Pi 2p/2, pi 2pz2, sigma 2px2. The 3 sigma star 2px, pi star 2py, pi star 2pz anti-bonding orbitals are vacant. All these anti-bonding orbitals are vacant. Hence, the molecule is highly stable because these having highest energy. If here electrons are there, that molecule will be destabilized. Anti-bonding orbitals are having highest energy. But all these are vacant. Hence, these are molecule having lot of stability. Only bonding molecular orbitals filled with electrons. Anti-bonding, all anti-bonding molecular orbitals are vacant. Here, in the nitrogen, as per molecular orbital energy level diagram of nitrogen molecule, there is no unpaired electrons are available here. Hence, nitrogen is the diamagnetic. It shows diamagnetism. Nitrogen molecule shows diamagnetism. Bond length is 1.1 angstrom unit. Bond dissociation energy is 945.6 kilojoule per mole. So like this, we will explain the bond order, magnetic property of the any diatomic, homonuclear diatomic molecule or heteronuclear diatomic molecules with the help of molecular orbital diagrams.